All right, this video is going over gas laws. Number one, we're going to list the properties of gases. First, gases are mostly empty space. Second, gases are made of tiny particles. Third, gases are compressible, meaning they can squish together. Gases are fluid-like. Just think of smoke rising from a fire. Then gases have an indefinite shape and an indefinite volume, meaning they can always change their shape and they can always change their volume. All right, number two, list the characteristics of an ideal gas. Well, ideal gas particles are always in a constant random motion. Next, gas particles undergo elastic collision, meaning no energy is lost. Gas particles occupy all available space. Gas particles are going to behave as if there's no volume. And gas particles exert no forces on each other. So they don't repel or attract each other. Number three, gas behavior is most ideal when the temperature is going to be high, so very hot, and if the pressure is low, so if there's no space for them to move around. Number four, what happens to kinetic energy of the gas particles when temperature decreases? So that means as it gets colder, the kinetic energy is going to decrease. That means the gas particles are going to move slower. Number five, what happens to kinetic energy of gas particles when temperature increases? So that means it's getting hotter. So the kinetic energy is going to increase. That means those gas particles are going to move faster and faster. Number six, what happens to the particles of matter when the temperature is absolute zero? So that means it cannot be any colder. And when that happens, all motion stops. All gas particles stop. So it freezes completely. Number seven, what law states that the number of moles and volume are related to each other? That's going to be Avogadro's law. Avogadro's law, moles and volume are going to be directly related. That means if the moles decrease, the volume will also decrease. All right, let's move over to number 8. What law states pressure and volume are related to each other? And that's Boyle's law. It states that pressure and volume are indirectly related. This is the only law that's indirectly related. Since they're indirectly related, they're opposite. That means if pressure decreases, volume's going to increase. Number 9, which law states that temperature and volume are related? That's Charles's law. This law states that temperature and volume are directly related. That means as temperature decreases, volume is also going to decrease. Number 10, which law relates pressure and temperature? That's Gay-Lussac's law. And it states that pressure and temperature are directly related. So if temperature decreases, pressure will also decrease. Number 11, what two things does STP tell us? STP means standard temperature and standard pressure. So the standard temperature that'll be 273 Kelvin. And then the standard pressure that'll be 1 atm. And remember, there's different pressures that we can use, but we're only going to focus on atmospheric pressure. Number 12, draw the graphs for the following relationships and name the law that applies to each. So pressure and volume, those are indirectly related. So if one goes down, the other's going to go up. This is what the graph will look like. And that's Boyle's law. Volume and temperature, directly related. So if one goes up, the other goes up. That's Charles' law. Volume in moles is also direct. If one goes up, the other goes up. That's Avogadro's law. And the last one, pressure and temperature, directly related. If one goes up, so does the other. That's Gay-Lussac's. Number 13, give the units for the following variables. Volume, that can be in liters or milliliters. Pressure, there's a lot of units to use for pressure, but we're just going to stick with atmospheres. T is for temperature, and that's going to always have to be in Kelvin. And N is for moles, that's MOL. All right, now we're going to go to the back. Number 14, give the formula for combined gas law. This law relates pressure, volume, and temperature, but we're also going to throw in moles in this equation. So it's going to be P1 V1 divided by N1 T1. That's first pressure times first volume divided by first moles times first temperature. And that's going to be equal to P2 times V2 divided by N2 times T2. And I'm just throwing moles in that equation so it can help us solve our other problems. Number 15, define and give the formula for Dalton's law. Dalton's law states that pressure exerted by a mixture of gases is equal to the sum of the partial pressures exerted by each of the gases. So that's a lot to write. Pressure exerted by a mixture of gases is equal to the sum of partial pressure exerted by each of the gases. I'm just going to put by each of the gases. And the formula is going to be our P total is going to equal P1 plus P2 plus P3, and we can keep adding or taking away as many pressures as we need to. So P total equals P1 plus P2 plus P3, and then again, it can keep going for as ever many pressures we need it to go to. Number 16, give the formula for ideal gas law. That's going to be our pressure times our volume is equal to our moles times our constant, R, multiplied by T. And R for the constant, since we're only using atmospheres this time, I'm going to write down that the R is always going to be our 0.0821. And I'm not going to write the units for that, but it's liters times atmospheres divided by moles times temperature. Number 17, how would you convert Celsius to Kelvin? And to convert Celsius to Kelvin, all you're going to do is add 273. So Kelvin is equal to whatever our degree Celsius is plus 273. So converting 25 degrees Celsius to Kelvin, we're just going to add 273 to that. So 25 plus 273, that's going to give us 298 Kelvin. Number 18, a gas with a volume of 9 liters contains a pressure of 5 atmospheres at 27 degrees Celsius. Calculate the number of moles of this gas. So we have our volume. Liters always measures volume. We have 5 atmospheres, that's our pressure, 5 atm. We have 27 degrees Celsius. Again, we don't use Celsius, we need to convert it to Kelvin, so we're going to add 273. So 27 plus 273, that's going to be 300. So our temperature is 300 Kelvin. And it's asking for the number of moles. We want to find the number of moles. So we're looking for our N. We're going to use our ideal gas formula to solve for this. So we're going to do our pressure times our volume. So 5 times 9. Equals, N is what we're looking for, times R, which is always 0.0821, multiplied by our temperature, which is 300. So to solve this problem, we're going to have to multiply 5 times 9. That's 45. and that's equal to our N, and then we're going to multiply 0.0821 times 300. That's 24.63. And I ran out of room, but we're going to divide both sides by 24.63. So 45 divided by 24.63, that's 1.827, which rounds to about 1.83. So our moles is 1.83. Number 19, an object is filled with 4 liters of air at 300 Kelvin. The object is then heated to 315 Kelvin. What is the new volume of the object, assuming constant pressure? So we have one volume, and we have one temperature that goes with it. So we can call that our V1 and our T1. And then it's heated to 315 Kelvin, so that can be our T2. And then we're looking for our new volume. So V2 is what we're looking for. So we're going to use the combined gas law. We only have volume and temperature, so we're only going to focus on the V1, T1, and the V2, T2. So we're going to cross out the M and N. So our formula will look like that. V1 over T1 equals V2 over T2. So plugging in our numbers, we have 4 liters divided by 300 equals our new volume, which we don't know what that is, divided by 315. And to solve this, we're going to do the butterfly method. We're going to multiply across. So these two numbers are across, so we're going to multiply 4 times 315. And that's 1,260. And then we're going to divide by the number that's left over. So divide by 300. That's 4.2. So our V2 equals 4.2. And since our first volume was liters, that means this will also be liters. All right, number 20. An object contains gas A at 60 atm, gas B at 100 atm, and gas C. The total pressure of the object is 200 atmospheres. What is the partial pressure of gas C? So we have our equation for gases. We're going to use Dalton's law, which is right here. P total equals P1 plus P2 plus P3. We only have 3 gases, A, B, and C, so we don't need to add any more than that. So our P total equals P1 plus P2 plus P3. Gas A is 60, so that can be our first P. Plus gas B is 100, so that can be our second P. And it just says gas C, it doesn't say anything about it. And then it says that the total pressure is 200. So we know our total is 200. So that means we're looking for our partial pressure of gas C. So we're looking for our P3. So to solve this problem first, we're going to add 60 and 100. That's 160. We still have our 200 on the left side, and we're adding it to P3. Since it's being added, to get rid of it, we're just going to subtract 160 from both sides. So 200 minus 160, that means P3 is 40. And that would be atmospheres, ATM. All right, let's go to number 21. An object holds 3 moles of gas So moles is our N of of gas at a volume of 2 liters. So we know that's our volume, 2 liters. To what volume will it expand if 2 moles of gas are added? So this is tricky wording. It says 2 moles of gas are added. So we originally have 3, but we're adding 2. So that means our N2 is going to be 3 plus 2, which is 5 moles. Pay attention to that keyword, are added. So that makes this our N1, our V1, and since we're looking for our new volume, that's going to be our V2 that we don't know. We're going to use our combined gas law again, and this is why I added the end. We're dealing with volume and moles, so we're going to use the V and the N. We're going to cross out the M and the T. We don't need those. So our equation's going to be V1 over N1 equals V2 over N2. So plugging that in, our V1 is 2, divided by our N1 is 3, equals our new volume that we don't know, divided by our new moles, which is 5. So to solve this problem again, we're going to multiply across. The 2 and the 5 are across. So we're going to do 2 times 5. And then we're going to divide it by the number that's left over. So divided by 3, that's going to be 3.33. So our V2 is 3.33. Since our first volume is liters, our second volume will also be liters. Number 22, an object has an initial pressure of 3 atmospheres. So we have our pressure. And an initial volume of 4 liters. So we have a volume. Its pressure changes to 2 atmospheres. So we have a new pressure. That means this was our first pressure and our first volume. So this will be our second pressure. What is the new volume? So I'm looking for my new volume if temperature and amount are kept constant. So I'm looking for my V2. So we have P's and V's. If I look at my combined gas law, I'm just going to focus on my P's and my V's. So that means I'm only going to do P1 V1 equals P2 V2. P1 is 3, V1 is 4, P2 is 2, and V2 is what I'm looking for. So 3 times 4 is 12. That's equal to 2 times V2. Then I'll divide both sides by 2. 12 divided by 2 is 6. So my V2 is 6. Since my first volume was liters, that means my final answer will also be liters. Number 23, a balloon holds gas at a pressure of 0.5 atmospheres. So that's my pressure. At a temperature of 25 degrees Celsius. Again, we don't use Celsius, so we're going to have to convert that to Kelvin. So 25 degrees Celsius plus 273. That's going to be 298 Kelvin. And then if the temperature is increased to 200 Celsius, so again, we need to change that. 200 plus 273 is 473 Kelvin. What will be the new pressure? So we're looking for P2. That means this was T2, that was T1, and this was P1. So we're dealing with pressure and temperature. If I take a look at the formula, I'm going to do P1 over T1. I don't need my N or my V equals P2 over T2. P1 over T1 equals P2 over T2. So P1 is 0.5, T1 is 298. I'm looking for my P2, and then my T2 is 473. I don't need K, sorry for that. So that means I'm going to multiply across. So I'm going to do 0.5 times 473. And then I'm going to divide by the number left over. So divided by 298. That means my new pressure is 0.793, which rounds to 0.79. So P2 equals 0.79, and my pressure is in atmospheres, ATM. Last question, a gas occupies a volume of 5 liters. So my volume's 5 liters. At standard temperature and pressure, STP. Remember, every time you're given STP, you know your standard temperature, which is 273 Kelvin, and you know your standard pressure, which is 1 ATM. That's always going to be STP. If the pressure is increased to 20 atmospheres, so we have a new pressure, 2.0 ATM, sorry. So that means that was our first pressure. And the temperature is increased to 150 degrees Celsius. So my T2 is 150 degrees Celsius, which we don't use Celsius. So we're going to have to turn that to Kelvin by adding 273. 150 plus 273, 423. That means that was my T1. What is the new volume? So I'm looking for my new volume. That means that was my first volume. So V2 is what I'm looking for. This time I have volume, temperature, and pressure. So I'm going to keep in my formula P1, V1, and T1. I just don't need N1. So that's going to be P1, V1 over T1 equals P2, V2 over T2. Plugging in my numbers, my first pressure is 1. My first volume is 5. Divided by my first temperature is 273. My second pressure is 2. I'm looking for that second volume. And my third temperature is my second temperature is 423. There's a lot to do. So first we're going to multiply 1 times 5 and divide it by 273. 1 times 5 divided by 273. That's about 0.0183. And then I'm going to do 2 divided by 4.23, and I'm going to leave the V2 there. That's 846. Oh, I'm sorry, divided. 2 divided by 423. That's about 0.004728. Running out of room there. Let's just write it on the side. So the first one was 0.083. Oh my gosh. 0.0183 equals 0.00472. Or 3. We'll just round it to 3. Equals V2. And then we'll divide both sides by the 0.00473. That cancels out over there. So I'm going to do 0.0183 divided by 0.00473. That gives me a 3.86 for my volume. I'll write my answer here. V2 equals 3.87, and that'll be liters. Sorry, that one was messy. All right, that is it for this review.